Chapter 14, Part 1 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook by the FAA. Transition to turbopropeller-powered airplanes. Part 1, General. The turbopropeller-powered airplane flies and handles just like any other airplane of comparable size and weight. The aerodynamics are the same. The major differences between flying a turboprop and other non-turbine-powered airplanes are found in the power plant and systems. The power plant is different and requires operating procedures that are unique to gas turbine engines. But so too are other systems such as the electrical system, hydraulics, environmental, flight control, rain and ice protection, and avionics. The turbopropeller-powered airplane also has the advantage of being equipped with a constant speed, full feathering, and reversing propeller, something normally not found on piston-powered airplanes. The gas turbine engine. Both piston, reciprocating engines and gas turbine engines are internal combustion engines. They have a similar cycle of operation that consists of induction, compression, combustion, expansion, and exhaust. In a piston engine, each of these events is a separate, distinct occurrence in each cylinder. Also, in a piston engine, an ignition event must occur during each cycle, in each cylinder. Unlike reciprocating engines, in gas turbine engines, these phases of power occur simultaneously and continuously, instead of one cycle at a time. Additionally, ignition occurs during the starting cycle and is continuous thereafter. The basic gas turbine engine contains 4 sections: intake, compression, combustion, and exhaust. See Figure 14-1. To start the engine, the compressor section is rotated by an electrical starter on small engines or an air-driven starter on large engines. As compressor RPM accelerates, air is brought in through the inlet duct, compressed to a high pressure, and delivered to the combustion section, combustion chambers. Fuel is then injected by a fuel controller through spray nozzles and ignited by igniter plugs. Not all of the compressed air is used to support combustion. Some of the compressed air bypasses the burner section and circulates within the engine to provide internal cooling. The fuel-air mixture in the combustion chamber is then burned in a continuous combustion process and produces a very high temperature, typically around 4,000 degrees Fahrenheit, which heats the entire air mass to 1,600 to 2,400 degrees Fahrenheit. The mixture of hot air and gases expands and is directed to the turbine blades, forcing the turbine section to rotate, which in turn drives the compressor by means of a direct shaft. After powering the turbine section, the high-velocity excess exhaust exits the tailpipe or exhaust section. Once the turbine section is powered by gases from the burner section, the starter is disengaged, and the igniters are turned off. Combustion continues until the engine is shut down by turning off the fuel supply. High-pressure exhaust gases can be used to provide jet thrust, as in a turbojet engine, or the gases can be directed through an additional turbine to drive a propeller through reduction gearing, as in a turbopropeller, turboprop engine. Turboprop engines. The turbojet engine excels the reciprocating engine in top speed and altitude performance. On the other hand, the turbojet engine has limited takeoff and initial climb performance, as compared to that of a reciprocating engine. In the matter of takeoff and initial climb performance, the reciprocating engine is superior to the turbojet engine. Turbojet engines are most efficient at high speeds and high altitudes, while propellers are most efficient at slow and medium speeds, less than 400 miles per hour. Propellers also improve takeoff and climb performance. The development of the turboprop engine was an attempt to combine in one engine the best characteristics of both the turbojet and propeller-driven reciprocating engine. The turboprop engine offers several advantages over other types of engines, such as lightweight, mechanical reliability due to relatively few moving parts, simplicity of operation, minimum vibration, high power per unit of weight, use of propeller for takeoff and landing. Turboprop engines are most efficient at speeds between 250 and 400 miles per hour, and altitudes between 18,000 and 30,000 feet. They also perform well at the slow speeds required for takeoff and landing, and are fuel efficient. The minimum specific fuel consumption of the turboprop engine is normally available in the altitude range of 25,000 feet up to the tropopause. The power output of a piston engine is measured in horsepower and is determined primarily by RPM and manifold pressure. The power of a turboprop engine, however, is measured in shaft horsepower, SHP. Shaft horsepower is determined by the RPM and the torque, twisting moment, applied to the propeller shaft. Since turboprop engines are gas turbine engines, some jet thrust is produced by exhaust leaving the engine. This thrust is added to the shaft horsepower to determine the total engine power, or equivalent shaft horsepower, ESHP. Jet thrust usually accounts for less than 10% of the total engine power. Although the turboprop engine is more complicated and heavier than a turbojet engine of equivalent size and power, it will deliver more thrust at low subsonic airspeeds. However, the advantages decrease as flight speed increases. In normal cruising speed ranges, the propulsive efficiency, output divided by input, of a turboprop decreases as speed increases. The propeller of a typical turboprop engine is responsible for roughly 90% of the total thrust under sea-level conditions on a standard day. The excellent performance of a turboprop during takeoff and climb is the result of the ability of the propeller to accelerate a large mass of air while the airplane is moving at a relatively low ground and flight speed. Turboprop, however, should not be confused with turbo-supercharged or similar terminology. All turbine engines have a similarity to normally aspirated, non-supercharged reciprocating engines, in that maximum available power decreases almost as a direct function of increased altitude. Although power will decrease as the airplane climbs to higher altitudes, engine efficiency in terms of specific fuel consumption, expressed as pounds of fuel consumed per horsepower per hour, will be increased. Decreased specific fuel consumption plus the increased true airspeed at higher altitudes is a definite advantage of a turboprop engine. All turbine engines, turboprop or turbojet, are defined by limiting temperatures, rotational speeds, and, in the case of turboprops, torque. Depending on the installation, the primary parameter for power setting might be temperature, torque, fuel flow, or RPM, either propeller RPM, gas generator, compressor RPM, or both. In cold weather conditions, torque limits can be exceeded, while temperature limits are still within acceptable range. While in hot weather conditions, temperature limits may be exceeded without exceeding torque limits. In any weather, the maximum power setting of a turbine engine is usually obtained with the throttles positioned somewhat aft of the full forward position. The transitioning pilot must understand the importance of knowing and observing limits on turbine engines. An over-temp or over-torque condition that lasts for more than a very few seconds can literally destroy internal engine components. Turboprop engine types. Fixed shaft. One type of turboprop engine is the fixed shaft constant speed type, such as the Garrett TPE 331. See Figure 14-2. In this type engine, ambient air is directed to the compressor section through the engine inlet. An acceleration-diffusion process in the two-stage compressor increases air pressure and directs it rearward to a combustor. The combustor is made up of a combustion chamber, a transition liner, and a turbine plenum. Atomized fuel is added to the air in the combustion chamber. Air also surrounds the combustion chamber to provide for cooling and insulation of the combustor. The gas mixture is initially ignited by high-energy igniter plugs, and the expanding combustion gases flow to the turbine. The energy of the hot, high-velocity gases is converted to torque on the main shaft by the turbine rotors. The reduction gear converts the high RPM, low torque of the main shaft to low RPM, high torque to drive the accessories and the propeller. The spent gases leaving the turbine are directed to the atmosphere by the exhaust pipe. Only about 10% of the air which passes through the engine is actually used in the combustion process. Up to approximately 20% of the compressed air may be bled off for the purpose of heating, cooling, cabin pressurization, and pneumatic systems. Over half the engine power is devoted to driving the compressor, and it is the compressor which can potentially produce very high drag in the case of a failed windmilling engine. In the fixed-shaft, constant-speed engine, the engine RPM may be varied within a narrow range of 96% to 100%. During ground operation, the RPM may be reduced to 70%. In flight, the engine operates at a constant speed, which is maintained by the governing section of the propeller. Power changes are made by increasing fuel flow and propeller blade angle rather than engine speed. An increase in fuel flow causes an increase in temperature and a corresponding increase in energy available to the turbine. The turbine absorbs more energy and transmits it to the propeller in the form of torque. The increased torque forces the propeller blade angle to be increased to maintain the constant speed. Turbine temperature is a very important factor to be considered in power production. It is directly related to fuel flow and thus to the power produced. It must be limited because of strength and durability of the material in the combustion and turbine section. The control system schedules fuel flow to produce specific temperatures and to limit those temperatures so that the temperature tolerances of the combustion and turbine sections are not exceeded. The engine is designed to operate for its entire life at 100%. All of its components, such as compressors and turbines, are most efficient when operated at or near the RPM design point. Power plant, engine, and propeller control is achieved by means of a power lever and a condition lever for each engine. See Figure 14-3. There is no mixture control and/or RPM lever as found on piston engine airplanes. On the fixed-shaft, constant-speed turboprop engine, the power lever is advanced or retarded to increase or decrease forward thrust. The power lever is also used to provide reverse thrust. The condition lever sets the desired engine RPM within a narrow range between that appropriate for ground operations and flight. Power plant instrumentation in a fixed-shaft turboprop engine typically consists of the following basic indicator. See Figure 14-4. Torque or horsepower, ITT, interturbine temperature, fuel flow, RPM. Torque developed by the turbine section is measured by a torque sensor. The torque is then reflected on a cockpit horsepower gauge, calibrated in horsepower times 100. Interturbine temperature, ITT, is a measurement of the combustion gas temperature between the first and second stages of the turbine section. The gauge is calibrated in degrees Celsius. Propeller RPM is reflected on a cockpit tachometer as a percentage of maximum RPM. Normally, a vernier indicator on the gauge dial indicates RPM in 1% graduations as well. The fuel flow indicator indicates fuel flow rate in pounds per hour. Propeller feathering in a fixed-shaft constant-speed turboprop engine is normally accomplished with the condition lever. An engine failure in this type engine, however, will result in a serious drag condition due to the large power requirements of the compressor being absorbed by the propeller. This could create a serious airplane control problem in twin-engine airplanes unless the failure is recognized immediately and the affected propeller feathered. For this reason, the fixed-shaft turboprop engine is equipped with negative torque sensing, NTS. Negative torque sensing is a condition wherein propeller torque drives the engine and the propeller is automatically driven to high pitch to reduce drag. The function of the negative torque sensing system is to limit the torque the engine can extract from the propeller during windmilling and thereby prevent large drag forces on the airplane. The NTS system causes a movement of the propeller blades automatically toward their feathered position, should the engine suddenly lose power while in flight. The NTS system is an emergency backup system in the event of sudden engine failure. It is not a substitution for the feathering device controlled by the condition lever. Split-shaft, free turbine engine. In a free-power turbine engine, such as a Pratt & Whitney PT6 engine, the propeller is driven by a separate turbine through reduction gearing. The propeller is not on the same shaft as the basic engine turbine and compressor. See Figure 14-5. Unlike the fixed-shaft engine, in the split-shaft engine, The propeller can be feathered in flight or on the ground with the basic engine still running. The free power turbine design allows the pilot to select a desired propeller governing RPM, regardless of basic engine RPM. A typical free power turbine engine has two independent counter-rotating turbines. One turbine drives the compressor, while the other drives the propeller through a reduction gearbox. The compressor in the basic engine consists of three axial flow compressor stages combined with a single centrifugal compressor stage. The axial and centrifugal stages are assembled on the same shaft and operate as a single unit. Inlet air enters the engine via a circular plenum near the rear of the engine and flows forward through the successive compressor stages. The flow is directed outward by the centrifugal compressor stage through radial diffusers before entering the combustion chamber, where the flow direction is actually reversed. The gases produced by combustion are once again reversed to expand forward through each turbine stage. After leaving the turbines, the gases are collected in a peripheral exhaust scroll and are discharged to the atmosphere through two exhaust ports near the front of the engine. A pneumatic fuel control system schedules fuel flow to maintain the power set by the gas generator power lever. Except in the beta range, propeller speed within the governing range remains constant at any selected propeller control lever position through the action of a propeller governor. The accessory drive at the aft end of the engine provides power to drive fuel pumps, fuel control, oil pumps, a starter generator, and a tachometer transmitter. At this point, the speed of the drive, N1, is the true speed of the compressor side of the engine, approximately 37,500 RPM. Power plant, engine, and propeller operation is achieved by three sets of controls for each engine: the power lever, propeller lever, and condition lever. See Figure 14-6. The power lever serves to control engine power in the range from idle through takeoff power. Forward or aft motion of the power lever increases or decreases gas generator RPM, N1, and thereby increases or decreases engine power. The propeller lever is operated conventionally and controls the constant speed propellers through the primary governor. The propeller RPM range is normally from 1,500 to 1,900. The condition lever controls the flow of fuel to the engine. Like the mixture lever in a piston-powered airplane, the condition lever is located at the far right of the power quadrant. But the condition lever on a turboprop engine is really just an on-off valve for delivering fuel. There are high idle and low idle positions for ground operations, but condition levers have no metering function. Leaning is not required in turbine engines. This function is performed automatically by a dedicated fuel control unit. Engine instruments in a split-shaft free turbine engine typically consist of the following basic indicators. See Figure 14-7. ITT, interstage turbine temperature indicator, torque meter, propeller tachometer, N1, gas generator tachometer, fuel flow indicator, oil temperature pressure indicator. The ITT indicator gives an instantaneous reading of engine gas temperature between the compressor turbine and the power turbines. The torque meter responds to power lever movement and gives an indication in foot-pounds, Ft/lb, of the torque being applied to the propeller. Because in the free turbine engine the propeller is not attached physically to the shaft of the gas turbine engine, two tachometers are justified, one for the propeller and one for the gas generator. The propeller tachometer is read directly in revolutions per minute. The N1, or gas generator, is read in percent of RPM. In the Pratt & Whitney PT6 engine, it is based on a figure of 37,000 RPM at 100%. Maximum continuous gas generator is limited to 38,100 RPM, or 101.5% N1. The ITT indicator and torque meter are used to set takeoff power. Climb and cruise power are established with the torque meter and propeller tachometer while observing ITT limits. Gas generator N1 operation is monitored by the gas generator tachometer. Proper observation and interpretation of these instruments provide an indication of engine performance and condition. End of Chapter 14, Part 1.